This is Module 13, Lecture Notes 25. As I'm sure you will talk about in class, this module is going to be done a little bit differently. In this lecture, I'm going to give you the background and some of the definitions to the thermodynamics chapter. Thermodynamics is a topic that can be very, very detailed, and it is almost always covered in great depth in a second-year chemistry course and then later on in college courses. Your book does do a nice job introducing some of the basics of thermodynamics. However, I don't think that we need to go into super detail in a first-year chemistry course with the thermodynamics chapter. So with that said, I'm going to give you some basics on it, like I said, and then you're actually going to spend a whole class period doing a lab on thermodynamics so that you can really get a hands-on feel for what it's like to have an energy change during a reaction. And then in this module will also be a formal lab report. So some of that class time will be used to work on your formal lab report. Okay, so in this lecture today, we're just going to do some of the basics. I'm going to break down this word thermodynamics for you. And when you think of the word thermo, I want you to think of heat. Okay, so thermodynamics is the study of heat. Okay, and it says in all chemical reactions, an energy change occurs. Well, where does that energy come from in a reaction? It is actually stored energy in the chemical bonds of the reactants and products. Okay, so picture you have two atoms joined together by a bond. When that bond is broken in a chemical reaction, energy is given off. Okay, and in most cases, we feel that energy in the form of heat. Okay, so we can fill in the blank by saying the energy stored in a substance is called the enthalpy. And you will often see it written as the change in H. Remember, the delta symbol means change, and an H is used to signify the change in heat or the change in enthalpy in a reaction. We have two types of reactions, and we've talked about this a little bit. One is called an endothermic reaction, and the other is an exothermic reaction. In an endothermic reaction, energy is absorbed. And so you will often feel cold to the touch for this type of reaction. Okay, so an example of an endothermic reaction that I can think of is like a cold pack. If you've ever seen one of those in like a first aid kit, it's like a packet and it has some different chemicals in it. And when you're ready to use it, you're supposed to squish the chemicals together and mix them. And that reaction absorbs energy and it feels cold to the touch. So it creates a cold pack. Okay. When we write this type of reaction, the energy is going to be written as a reactant. And so that means it will be written on the left side of the reaction. And we'll practice with some of these later on. And the change in enthalpy is going to be positive for these type of reactions. Okay, so these main things about endothermic reactions are something that you should memorize. You could put them on a flashcard or just practice them lots and lots. And they're going to be opposites to the exothermic reactions. So for exothermic reactions, instead of absorbing energy, energy is going to be released or given off. So naturally, they're going to feel hot to the touch. Okay, And one of the reactions that you've done in class is when you use toilet bowl cleaner or drain cleaner, and I think you added some aluminum foil to it, and it got really bubbly and really hot. That was definitely an exothermic reaction because it was releasing energy. Energy will be written as a product, and the enthalpy is going to be negative for exothermic reactions. Okay, so you might want to write yourself a note that these are things you need to know about endothermic and exothermic reactions. Okay, so let's look at two practice problems, how we can combine what we already know about writing and balancing reactions from several units ago to what we just learned about endothermic and exothermic reactions. Okay, if you need to brush up on reaction writing, I'm going to refer you back to Module 5. And you should have notes there on reaction types and balancing and that sort of thing. But we'll work through this one together, and I think it should come back to you. So this says in the formation, that is a key word. In the formation of H2SO4, 814 kilojoules of heat are absorbed. Is this an endothermic or exothermic reaction? When energy is absorbed, we know it's an endothermic reaction. So why don't we make note of that, and we'll come back to that after we write our reaction. So we need to do the formation of H2SO4, and formation means that we have all of the individual elements coming together to form H2SO4. Okay, so we know we have hydrogen plus some sulfur plus some oxygen, and they're going to come together to form H2SO4. Now, why did I write H2 and O2 with 2's after them, but I didn't for sulfur? Do you remember that rule we learned about the 7 diatomics that can never be by themselves? Okay, that rule still applies. Hydrogen and oxygen both are diatomic gases. So I have H2 plus sulfur, it can be by itself, plus O2 forming H2SO4. Now I'm going to balance this. Let's see, I have H2 on both sides, I have S on both sides, but my oxygens are not balanced. So I think I just need a 2 right here, and everything will be balanced. Well, hey, that was pretty easy because that's all review. Now, the only part we need to add to this to completely answer the question is it says write and balance the reaction adding energy as a reactant or product. So we know this is an endothermic reaction, and that means energy is going to be absorbed. It is a reactant. It takes some energy to form these things to produce the product. So the last thing you have to do is you need to put the 814 kilojoules of heat on the reactant side. These things plus some heat come together to form our sulfuric acid over here. Okay? And then if you want to go a little bit further, you could always write the delta H of the whole reaction. And from our definitions, we know it's going to be a positive number. So you could just say the delta H is 814 kilojoules. That's how you would completely answer one of these new problems. Okay, let's look at the second problem together. Before we go through it, you do need to make a small change to the problem itself. It says the decomposition of K3PO4 has a delta H of negative 2030 kilojoules. Please make sure you make that note before we get into the problem. All right, so decomposition. Remember, when something decomposes, it breaks apart. So we're going to take our K3PO4 and we're going to split it up. It's going to decompose into potassium, it can be by itself, plus phosphorus, plus oxygen, which is always a diatomic. Okay, again, if you need to brush up on these two definitions, go back to Module 5. Next, you should balance your reaction. Let's see, I have 4 oxygens here, and I have 2 over there. So let's put a 2 here. I have 3 potassium on each side now, and we'll do 1 phosphorus. So that should be good. Now, which side of the reaction should I be adding the heat to? It's negative 2030 kilojoules. Up here in our definitions, negative delta H tells us that this is an exothermic reaction. The heat is released as a product. So you're going to add heat onto the product side. Okay? Now, this can be a little bit confusing. The heat number itself is negative, but because you're putting it on the product side, you still write it as plus 2030 kilojoules. Potassium phosphate breaks apart into potassium, phosphorus, oxygen, and heat is released. Okay? You can write here that this one is exothermic. Heat is given off, and so the delta H is negative for an exothermic reaction. On the other side of your paper, we're going to look at some graphs, and these are specifically called energy diagrams. Okay? These energy diagrams show chemists what is happening in a chemical reaction in terms of energy. Okay? So energy is here on your y-axis, and then on your x-axis is the progress of the reaction. This would be the start of the reaction, and this would be the end, or when the reaction is finishing, and it goes on throughout time. Okay, another vocabulary word that we need to talk about is something called activation energy. And this is the energy needed to start a chemical reaction, to get it going. Okay, and in a graph, it is really easy to see the activation energy. Okay, so in these two graphs here, you can see that they both have a hump in them. Okay, in this first graph, the activation energy is right here. Okay, it is the energy needed to go from reactants, start up the reaction, and finish at products. It takes energy to go from one to the other. Okay, and in the second graph, the activation energy is quite large, and it's much larger. It is this distance here that you can label as activation energy. Okay, so for these two graphs, we need to label one of them an endothermic reaction and one of them an exothermic reaction. So let's read these definitions off to the side. In this one, the reactants have more energy than the products. Okay, let me say that again. The reactants start off at a higher energy than the products. So therefore, after the reaction is complete, energy is given off to the surroundings in the form of heat. Okay, so heat is given off after the reaction. Jump back to your first page and think about what kind of reaction that describes. Is it endothermic or exothermic? This describes an exothermic reaction because heat is given off to the surroundings. Okay, and in the second graph, it says the products have more energy than the reactants. So the reactants need to absorb energy to get over this activation energy barrier. They absorb energy from the surroundings. So energy is coming in order for the reaction to happen. And so this would be an endothermic reaction. Endo reaction. No, sorry, I can't write and talk at the same time. Endothermic. Okay, so hopefully that helps give you a visual of what it looks like in a graphing sense to go from reactants to products giving off heat and going from reactants to products absorbing heat to get to your final product. Thanks for listening, guys, and I hope you have a great time doing your lab together in class. Have a lot of fun.